Aloha, phenomenal phoenixes. So, there's a couple of things I want you to know, to understand, and some things to do in this lesson. We're going to learn about scaling. That is, taking something very large and scaling it down smaller, but making sure that it maintains all that makes it its shape. Or blowing something up and making it larger. All of that is called scaling. All right. And to really grasp this idea, we're going to be looking at what makes something a similar shape. In other words, you got the small thing and then a large thing. They're similar shapes. It's just one has been blown up or one has been uh, shrunk down. And so we're going to see mathematically what it is about that shape that is preserved when you blow it up or when you shrink it down. And that is mainly like the angles remain the same as far as what we're looking at today. And there's a relationship that stays the same in the lengths of that shape. And that's what this is saying right here. Similar shapes maintain the proportional relationship. That's what stays the same as they grow up. These or as they're blown up or as they shrink, what's maintained is the relationship of the lengths. I'll go into that more. You'll see. Now, what we're going to do, what you're going to be able to do, is determine whether shapes are similar, and if I give you two shapes that are similar, you're going to be able to make some conclusions about the scaling. Did I scale it right? Did I scale it wrong? And then if they're not similar, you're going to be able to make some similar conclusions about it. All right, so that's where we're headed. Let's go. All right, last week we talked about transformations, or at least you watched some videos on transformations. Remember, these are 2D images like this map, and they're like placed on a plane, like a coordinate plane, right? And we learned that rigid transformations are shifting or rotating a shape or reflecting a shape. And those were rigid transformations. But now we're looking at a transformation that is not rigid, which is, again, scaling. And that looks like having a gigantic California, thousands of miles long, and shrinking it down, scaling it down to a smaller map. To get this big land to this small image, the original to this small image, meant zooming down or shrinking, scaling by hundreds of thousands of times. It was 100,000s of times smaller. So that maybe this stretch this stretch of land right here, maybe on this map right here is like, I don't know, 5 inches, right? Well, if we have to shrink it down, I don't know, maybe even let's say a million times, then let's say this is that part of the land right here. Might be hard to see on the video. Um, if we're shrinking it down a million times, then we know that this is probably 5 million inches up here, right? So there's this consistent shrinking of all parts of California to get it to be this map. Now, it doesn't matter like what direction you go in a scaling. You could start with some small little 2-inch stickers of Kansas City Chiefs and the Eagles, and you could blow that up into large, like real life size stickers, again, 2 dimensional, and that would be a scaling. But here's the really important thing to get, guys. When you're scaling, when you're making everything 5 times larger, 20 times larger, or 30 times smaller, 100 times smaller, you have to make every length must get that much smaller. Everything that's measured in length must be, if you're scaling 3 times smaller, then every length must get 3 times smaller. This is the most important thing to get from this. And there's a lot you can do when you understand this. So look at some examples of where this is not, where I'm doing this, this is not the case. Look at these stickers. Sure, they were blown up, right? But like this length blew up to this super large length. I don't know, maybe that's like 8 times larger. So this length got like 8 times larger. But you'll see the width right here, the length of the width, how long it is, it barely got any bigger at all. Everything, every length did not get 8 times larger. There wasn't a consistency. And you can see over here, It got way wide, but it didn't also get long. And you'll see this, everything that you can measure in length, if you're making it 10 times bigger, every length must also be 10 times bigger. Every length. So, like I said, this applies to every single part, guys. So let's say we are, ignore for right now these numbers. We'll get to that. But let's just say for the fun of it that we want to make an action figure out of Ben Affleck's Batman. And so, it looks like we have to like pretty much half it. We gotta we gotta divide by two to get to this kind of like huge huge action figure of Batman. So we're gonna say we have to shrink it. We have to shrink it 1.5 times. Or another way to say that is I have to divide it by one half, one and a half. Sorry. Either way you want to look at it. Okay, it's getting 1.5 times smaller. Ignore for the moment that this Batman is not wearing the right clothes, so that right, it's different colors and whatnot. But this, this let's not get stuck in the weeds, okay? All right, come on. Remember this idea that everything that gets scaled, everything in this picture must be scaled. So that means, like, if this is Ben Affleck's waist, and I imagine his waist is probably a 36-inch waist, maybe 34, because that's pretty average. Okay, then it must be shrunk by 1.5 to get this waist. All right, so shrunk by 1.5 means that that smaller Batman, his waist should be about 24 inches. Now, look, you can even just by sight, you can see that like Ben Affleck's chest measurement, like proportional to his head. Look at his head here. Like it's like maybe what, like twice as large as his head, right? Look over here. Look how wide his chest is relative to this skinny little head. All right. It's not the same. That relationship should stay the same. His chest is way too big. And in fact, that's ultimately what these numbers mean, guys. What these numbers mean is if this action figure was blown up to actual size, then Ben Affleck's biceps would be 26 inches. And that's like larger than Arnold Schwarzenegger's were. They'd be gigantic. Um, his chest would be 57 inches. And I guarantee you it's more like 48 in this picture. And his waist would be 30 inches, but we already know Ben Affleck's probably got like a 36-inch waist. So the proportions are all messed up. All right. That's the point. The point is, every if we're gonna make this thing scale down 1.5, every little part should scale down 1.5. Or if we're gonna make this scale up 1.5, every part, every length of everything should scale up 1.5 as well. And if in this original picture the head is like a third or a half of the chest, then down here it should also be a third or a half as well. And that touches on this idea of proportionality, which we'll talk about more.